When we want to calculate standard enthalpy change for a reaction, we need to have access to that table, heats of formation table, either in your appendix or from printing this particular PowerPoint. But any reaction can be written as the sum of formation of reactions. That's Hess's law, or the reverse of formation of reactions. Again, Hess's law, if you flip the direction, we simply flip the sign. So instead of using Hess's law, as tedious that might be, although I find enjoyable, we've come up with an easier way to find a target equation, and that's simply taking the sum of the products minus reactants. Products minus reactants will find the sum of the heat of reaction. That sigma stands for sum, and it's a Greek symbol. Perhaps you're familiar with it. N is the coefficient in front of each product or reactant. So using our standard heats of formation, we're able to calculate a little easier than using Hess's law. Let's model with this example on slide 41. Methane gas plus oxygen gas, this is a combustion pattern, produce carbon dioxide gas and water gas. This is a balanced equation with a 1 to 2 to 1 to 2 equation. We need to repair that coefficient. Let's go to work and see if my PowerPoint slide has enough or if I have to pull out the back of our chemistry book. Methane is CH4 as a gas. I go to work and I find its value. And I'm just going to write it for now right underneath the equation. I'm going to write negative 74.6. And that's in a kilojoule. Diatomic molecular oxygen is 0. Again, just showing that we know oxygen in its natural state, here it is 0, O2 gas. And again, I would distribute the 2. 2 times 0 is still 0. Carbon dioxide gas, going to our chart, CO2 gas, negative 393.5. And how about water gas, H2O? And water is listed under the oxygen. Water as a gas, negative 241.8, but I have to distribute the 2 through that. All right, so coefficient times the number from our chart. Simply stated, if I want to calculate the heat of this reaction, it's the sum, and I'm not very good at drawing those sigmas, the sum of the products minus reactants. So, products first. I'm going to take negative 393.5 plus 2 times negative 241.8. The sum of the products minus the sum of the reactants. Negative 74.6 plus 0. So here's what we have, just to kind of clarify. First big bracket is product minus reactant. Let's hit on our calculator and see if we can get a common answer. All right, so first set of parentheses, negative 393.5 plus 2 times negative 241.8, close your parentheses out, minus negative 74.6 equals. And I found the heat of this reaction to be negative 802.5 kilojoules of heat. These problems simply have us take time with the standard enthalpies of formation chart, either using your appendix or the slide from the PowerPoint, finding the values, and I just record them underneath just to help me tabulate. I have to distribute the coefficients through. I sum the products and I subtract the sum of the reactants. Products minus reactants will pull out the Kj, the heat of energy for that reaction. Why don't you try one and see if we can reach a common answer, pausing the video and working ahead, turning it back on when ready to check. Here we have C2H2 as a gas. Again, I'm just going to use my chart and find C2H2 is positive 227.4. 227.4. I'll know I'll have to distribute through 2 times that value. It is a positive. Oxygen, again, in its natural state is 0. Carbon dioxide gas, we looked up, negative 393.5. Remembering to distribute a 4 through that value from the coefficient. And now liquid water, negative 285.8. Distribute a 2 through that. The heat of this reaction is the sum of products minus reactants. So I'll just set up my math. The heat of the reaction is found by taking 4 times negative 393.5 plus 2 times negative 285.8. The sum of the products minus 2 times 227.4. And there's the sum of the reactants. Products minus reactants. Let's hit together and see what we find. We have 4 times negative 393.5 plus 2 times negative 285.8 minus 2 times 227.4. We get a value of an exothermic negative 2600.4 kilojoules of heat. Products minus reactants, distributing the coefficients, and simply taking some time to look through the standard enthalpy chart to find your equation. How many kilograms of octane, is this on the right slide? Looks like it. How many kilograms of octane, C8H18, that's gasoline, must be combusted? So add oxygen, out comes carbon dioxide and water, to supply 1 times 10 to the 11th kilojoules of energy. Well, let's balance as I'm counting in my head. 8 carbons, try an 8 there. 18 hydrogens, so I'll try a 9 here. That's going to give me an odd number of oxygens, which is completely fine if we want to care. We have 8 times 2 is 16, plus 9 is 25. To put a whole number here wouldn't make sense because I can't get O2 to add to 25, but I can do a little trick. It's 25 halves. And I don't mind doing that because the heat of formation for oxygen is 0. Any number times 0 is going to stay 0, and yet this still allows me to balance the equation. Alrighty. So, how many kilograms of octane? I guess we're ultimately trying to solve for octane, C8H18. C8H18 isn't on our list, C8H18, but we can solve for it. So suppose the delta H for this reaction is 1 times 10 to the 11th kilojoule, and that's for every 1 mole of octane. Alrighty. If this particular reaction per mole releases 1 times 10 to the 11th kJs, how many kilograms would be released? I look at this more as stoichiometry than really with the enthalpy chart. So if I know that 1 times 10 to the 11th kilojoules of heat are released, I don't really know that. I'm going to pause. Let's think this through. What I don't know is that's the delta H because it does not say that it's in kilojoules of heat. Alrighty. But what if I solved for this, making this the target? I can find out how many moles or kilojoules of octane must be there. If 1 times 10 to the 11th is the heat of the reaction, the sum of the products minus